So with variable stars, pulsating variable stars, you had pulsating stars. And why would stars pulsate? What would make them get bigger and smaller and bigger and smaller? And what happened was that a fellow by the name of Arthur Eddington, Sir Arthur Eddington, worked out the mathematics of how a star would pulsate. And so what he did was he realized that you could explain how stars pulsate. So what he realized was that stars are made of hydrogen and helium. And so you've got a star, and as you get deeper inside of the star, you can have a region here of the star that's just the right temperature and pressure that the helium can be ionized. And so all the heat is being produced in the center of the star. And so as this is trying to get out, you normally think of gases like hydrogen or helium as being transparent. You think of air as transparent, but it's not entirely always transparent. It's transparent under certain circumstances. If you change the temperature and the pressure, then it might not be. And so what would happen is this layer would be non-transparent and would be heating up. When it heats up, it expands. When it expands, then it causes the outer part of the star to expand. And so as the outer part of the star expanded, then the gas would cool off. And so the star would get big and would get kind of red. Well, what eventually happened, though, was this layer, because it expanded, was a different temperature and pressure. And then what would happen is that it would become transparent to the light. And so the energy would go right through, and it'd be giving off its energy and cooling off. It would compact. It'd get smaller. And as it got smaller, then the outer part of the star would get pulled back in. And when you do, you're squeezing the gas. When you squeeze the gas, it gets hotter. So what would happen is the star would get small and hot, or big and cool. And so we know that the luminosity, the brightness of the star, depends on the area and depends on the temperature. And so the luminosity, remember we said that luminosity was equal to the Stefan-Boltzmann constant times the area times the temperature to the fourth power. Okay. And so what that means is that when it gets bigger, that would make it look like it's going to get brighter, but when it gets hotter, that makes it look brighter. So this is to the fourth power, so that actually dominates over the area. And so when it gets smaller, it's actually brighter than when it gets big. And so up here we have these graphs, for example, of one of these stars, and the graphs show that the magnitude, remember small number up here at the top means brighter, so it gets bright and then gets dim. It gets bright and gets dim. And so what's happening is that the temperature is getting hot, cool, okay? The size is small, big, small, big. And then it's getting bigger, getting smaller, getting bigger, and so forth. And so that's what these graphs are trying to tell you. Okay. The prototype of the Cepheid variables is in fact Delta Cepheus. And remember, that's one of the first variable stars discovered was Delta Cepheus. And so the Cepheid variables are any type of variable star that varies in the same fashion as Delta Cepheus. And so the stars get brighter and dimmer. They tend to get brighter quicker than they get dim. And so your typical Cepheid variable varies in about a week or two, getting bright to dim and then bright again. So going through a complete cycle in 1 or 2 weeks. There are variations. Some can do it in just a day or two, and some of them can do it in a month or two. But your average one is a week or so. And most of these are supergiants. They're spectral type F when they're at max brightness, and spectral type G when they're minimum. They tend to vary between 0.1 and 2 magnitudes. So that's the typical characteristics. Now, there's an interesting story here. One of these women that Ed Pickering hired was Henrietta Leavitt. And Henrietta Leavitt was working on variable stars there at Harvard, but they had an observatory in the southern hemisphere down in Chile, and it was looking at Cepheid variables and other kind of stars in the southern hemisphere in a satellite galaxy that actually orbits around the rest of our galaxy. So we have our galaxy and a little satellite galaxy out here. So even though the satellite galaxy is pretty big, all the stars are almost the same distance percentage-wise from us. And what they needed was somebody down there to do a lot of the just basic data collection, data analysis, and tabulating and recording stuff and analyzing things. The astronomers would collect the data during the night, and then someone during the day had to do a lot of the work. And so she volunteered to go down there, and she actually spent almost a year in Chile working on this. And what she did was she was looking at the Cepheid variables, and she said, well, I need to organize Cepheid variables in some fashion. And she said, well, how do I organize this? Well, I want to make a list of them. And so she said, well, how do I organize my list? And so what she did was she said, I'm going to try several different ways of organizing and see which way works best. Okay, you don't want to do it alphabetically. You want to organize in some of the fashion. So what she did was she made a list based on magnitudes. Bright to dim. And then she made a list based on period, how long it takes to go through a complete cycle, from long period to short period. And then she discovered a really interesting thing. The two lists were identical. So there was a direct relationship between the magnitude of a Cepheid variable and the period. Well, because all of these things are almost the same distance away, we know that absolute magnitude is apparent magnitude plus 5 minus 5 log d. So the d doesn't change much, and so therefore bigger magnitude meant bigger absolute magnitude. Smaller magnitude meant smaller absolute magnitude. So the absolute magnitude was directly related to the luminosity, which is the actual power output of the star. And so what that meant was that she had realized that the power output of the star was directly related to how long it took to pulsate. And so we have the period luminosity relationship. And so it looks like a fairly straight line. Okay, well, it's sort of what you do is this is a log-log graph. So what you take is take the log of the period and plot on the x-axis, take the log of the luminosity, plot on the y-axis, and then you get a straight line. So it's not just, you know, a straight graph. But she realized if you plot it this way, it works fantastic. So what you would do is you could then look at a Cepheid variable, figure out what the period is, go up to this graph, okay, and then you just come over and find the luminosity. Well, if you know the luminosity, you also know the absolute magnitude. Well, why is that important? Because if you know the absolute magnitude, you can now plug into our formula here that we've used a couple times, apparent magnitude minus absolute magnitude plus 5, then you divide by 5, 10 raised to this exponent, that's not multiplied, that's raised into an exponent, and that gives you the distance. Now, why do we care? Because if something is too far away for parallax, this is the only way of finding the distance. And so we could only measure parallax at the time for pretty nearby stars. This allowed us to measure distances to very, very distant stars. Well, that turned out to be a major deal. as soon as she made her discovery, then Harlow Shapley used her relationship, and he started measuring distances to Cepheid variables in globular clusters. Now, they knew that globular clusters actually form a halo that surrounds the rest of our galaxy. And so this halo surrounds the rest of the galaxy, and so the idea would be it'd be centered on the center of the galaxy. Well, at the time, everybody thought the entire galaxy was maybe 10,000 light years across, maybe about 3,000 light years thick, you know, like a big fat pancake, and we were near the middle of it because that's all that we could see. And so they were trying to figure out how far from the middle we were. And so he started measuring distances to all these globular clusters. And what he realized was they were not centered on the sun. They were centered on a spot that was about 25,000 light years away, beyond what they thought was the edge of the universe, because they didn't know there was anything outside of a galaxy at the time. They thought the entire universe was about 10,000 light years across and about 3,000 light years thick. And he was finding that the center of this swarm of these things was 25,000 light years away. So this was a major step forward in understanding how the universe works. Well, just a few years later, Edwin Hubble makes a discovery, and that is in this big swirly thing here, which most people just call the Great Nebula in Andromeda. They thought that this Great Nebula in Andromeda was a swirl of gas coming together to make stars about 500 light years away. And so he, using the new telescope at Mount Wilson that George Ellery Hale got built, discovered on the outer edges of it a variable star that got brighter and dimmer like a Cepheid variable. And so what he did was he measured how long it took to get brighter and dimmer, and then using Henrietta and Leavitt's relationship, he was able to find the absolute magnitude of it. Once he had the absolute magnitude of it, then what happens is he was able to find the distance. And he found that this great spiral nebula in Andromeda was actually about 2.5 million light years away, which means in order to be as big as it is in the sky, it had to be at least as big as our own galaxy. In other words, it was a galaxy like our own galaxy. And then he started finding these Cepheids in other big swirly things out there and found that they were galaxies that were even farther away, tens of millions of light years away. All of a sudden, Henrietta Leavitt's discovery suddenly rocked astronomy, because now astronomers were discovering that the entire universe, instead of being 10,000 light years across, was made up of these giant galaxies that were bigger than we thought the whole universe was, and each one of them is millions of light years away from the other. And so it totally revolutionized our understanding of the universe. Later, Walter Baade realized you can fine-tune the whole thing, because it turns out there's two types of Cepheids. Type 1 Cepheids, that's population 1 stars, and type 2 Cepheids, which are population 2 stars. So there's a slightly different period luminosity relationship, but we're not going to worry about that. You just should know that population 1 stars and population 2 stars, when they become Cepheids, are just a tiny bit different. There's not a huge thing you need to know there, you know, for this level, this class, just they are slightly different.